Hello and welcome back to another edition of our Down and Dirty mini movies. We're up to video number 17 now in our short film help series, where I basically bring you short videos of, a lot of times it's just software features to help you as a salesman better understand the software, be able to talk more intelligently and demonstrate it, and then for the end user to hopefully have a better experience with the product. Today, we're going to be talking about surveying in state plane coordinates, and I've been asked to set up a grid-to-ground transformation in magnet field. Now, this video is a lot more technical. There's going to be a lot more talking because if you're not familiar with this, there's a lot more to really understand what's going on in the background. Magnet field makes it really simple, but you do need to understand what's going on. Now, all the techniques expressed or implied in this video are for examples only. This video is to show features of the software, and it's not meant to be used to set any precedents on how you should perform a particular survey function or how that would be performed on an actual job site. That's up to the sole description of the professional that's running the equipment out in the field. Now, if you're coming from the machine control side and you're probably used to using Pocket 3D and you probably localize and been trained to localize on every particular job, and that's fine. You're working on a particular system, localization scales to that system, whether that's in meters, ground, state plane, whatever. Localization scales and rotates to that system. You're on it. And as long as you stay with the equipment on that system, everything you do is fine. But think of it like a mapping scale of 1 to 100 that might be on the ground versus a scale of 1 to 200 on a state plane. As long as you stay with either one of those systems, it's accurate, but you can't use a scale of 1 to measure on the plane of the other one. Now, magnet field, talk about it for a second, treats localization as a ground system. So it's going to scale and rotate to that, but it thinks it's on a ground system. It doesn't really think of them as state plane coordinates anymore if you're localized to a state plane system. So the problem you get into is if you're measuring with an optical system, it's going to possibly scale that on the ground. But magnet field has already scaled it to a state plane. You're going to have issues. If I wanted to work with a job that was created in state plane, in my AutoCAD, I would scale that job from state plane to a ground system, send it out to the data collector. I would localize that way. Then if I measure between GPS and ground, I'd be good either way. But unfortunately, a lot of your jobs that you run into are designed in state plane, and that's what you want to work in. So in magnet field, when using a GPS basin rover, my suggestion is to set up the correct state plane datum, occupy one GPS point, and go. The reason being is the projections are already set in there, and it's kind of like its own localization within itself, meaning you set the base up on one point, it's going to know the scale and rotation. You should be able to stake out every other point and hit it right on the money. Hopefully your control was set within, let's say, a half a centimeter if it was done with static post-processing. So you're starting off on a very accurate point. As soon as you localize, go the opposite way, you're shooting a point that you're trying to get localized on. With GPS rover that's only good within 1 to 2 centimeters, you may be degrading your system going forward. So just a suggestion, it's not telling you what to do. So let's talk a little bit about the job that we're going to be using in magnet field. Now this is a job that's going to be set up in state plane coordinate system in Georgia West. We have control here, 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 and here. These are all about 1,500 feet apart. And we're going to be surveying, measuring with both GPS and optical, primarily with optical, between D11 and D17. And we're going to be talking about our grid to ground from there. Now let's take a look at this from a profile standpoint. You noticed we've got elevations ranging, I think our lowest point is 983 up to 998. This is our topographic surface, and you'll see later in the video I'm going to use point number D12 as an origin point. And we're going to be talking about why, because this is an elevation that's mean between D11 and D17. So let's get a little bit more in depth on this information. So a lot of information here, and if you want to learn more about state plane coordinates, this is one link that you can go. There's plenty of them on the web that describes this in more detail. But if you noticed here, we're going to be measuring between D11 and D17 with a horizontal ground distance, 1574.06. When we measure our grid distance, 1573.86, there's two tenths of a foot difference between a grid distance and a ground distance. And the reason being is this point here, with gravity, this line goes to the center of the earth. Same thing with D17. This line that we see here based on gravity goes to the center of the earth. Your mapping plane, which is your state plane projection, is projected basically down here where it fits close to the ellipsoid. So that distance is definitely going to be shorter. You know, your GPS is rotating way up here, and all of the GPS positions are based on what's called an Earth-centered, Earth-fixed coordinate. So they basically use different ellipsoids to calculate how to get up to here. What we need to know is scale factors for whatever mapping plane you're on, and then also we need to know what elevation is so it can calculate an elevation factor. These two together gives us a combined scale factor. Quite technical. Magnet field makes it very simple. The only thing I'm going to point out here that I may miss later in the video is the fact when I choose D12, again as the origin point, it's close to halfway in between these two elevations, because a difference in elevation factor will change the scale factor to use to go between your grid distances and your ground distances. So one other thought I would say is if you're working maybe in this location primarily, you may want to separate your job so you work with one scale factor here, maybe work with another job with a different scale factor for this segment of stationing through this part of the job site. It just depends on how much difference in elevation that you have. Okay? So I know we're getting pretty technical with this particular sales demo presentation, but it's just because of the nature of the beast. But I do refer all of training. Go back to elearning.topcon.com for true training lessons. Topcon has professionals that are geared more for true training. And then always check out tons of information on the MyTopcon Now app on your phone, but you can also get that from your browser, mytopconnow.topconpositioning.com. So without further ado, let's get started. So I'm in Magnet Field. I've got a default job set up, but I'm going to create us a brand new job so we can actually start it with the correct mapping datum set properly, and then just build from there. We're running Magnet Field version 6.2, might be the beta version, but I can't talk about that. We're going to go up to Job, create us a new job, call this one number 17. We got our simulations and everything set up here. Let's go next. Then my projection, we're going to be in Georgia West. And I'm going to choose no transformation. Now we're going to come back to this a little bit later, and we'll set up a grid to ground definition. And I want to go ahead and give me a little bit more distance precision here since we're working with grid coordinates. I think everything else is going to be good, so let's just begin from there. I have it set up to bring in my quick code, so I'm coming from a job that has quick code, so they're being imported. Next, we don't have any points in this particular job. Let's go grab the control that was brought in, processed by static data. So we'll go from a file, and this is a Excel file, northeast and zenith. I don't believe there's any setting. We'll just bring them in as design points. That's fine. And I've got them in east, north, zenith, or north NEZ. So NEZ is what we want. That's the grid I believe they're in, so we should be good. So we have our 22 points brought into the job. So here, under Edit, Points, we can view them. Now one thing I want to mention is when you go to the little different view icon, you remember this from the previous video, we can change our views from grid to different things now. I don't see datum listed here. I guess that's by design, but because I can tell we're hooked up to a total station, I'm not seeing an option to pick my datum, latitude, longitude, and height, nor anything else. I'll show you how that changes just a little bit later when we proceed. One thing I want to do is calculate an inverse and just double check that I've got my points in here properly. So I'm going to go to the map and I'm going to inverse between 11 and 17. So here is my grid bearing. This is on the grid, and this is my grid distance. Let's compare this distance with the map in my presentation. And we see that it matches 1573.859. That is our grid distance. Now this will change when we set up our ground definition. We not only will have it defined as a grid inverse, but also a ground. And then on both of our inverses that you'll see even later on, you'll see this geodetic information, geodetic bearing and geodetic distance. I doubt you would ever use this, but don't get this confused with a ground distance. This is not a ground distance, okay? So if I was going to survey with GPS, I would, let's say it's a base rover, this is how I would proceed. Let's disconnect from our total station for a minute, connect to our GNSS, and let's say we're doing a base rover setup. So we'll connect our base. I would occupy point number D11. Now notice that it populates and fills in all the information. It reads that just fine. I would type in the antenna height, 7.62. And that is a slant height for my base. So I put the base receiver on a control point and I would start base. Base started successful, go to the rover, say yes. I would connect to my rover and I'm ready to go. I think this is probably more accurate since I'm coming off of a known control. That's probably was set with an area of ellipse of within about really probably half a centimeter, and then you're going to be topoing from there. So we go right into survey and topo. We're ready to survey. We're on this point. We've got our state plane coordinates, and everything we shoot would be on state plane grid and so forth. Same way with staking out. So now let's set up a grid to ground so we can run this with a total station. We want to measure with a total station. So this time I will go to configure, back to my coordinate system, and I'll check on grid to ground. And then I need to define how this is going to be calculated. So we'll go into here. Now in the grid to ground parameters, we have a couple of options here. We have an average job height, If we knew the mapping scale factor, we would type that in here and the average job height. I don't have that information. If I knew the scale factor, I could put in the grid to ground scale factor and be good to go. What I do have is origin information. So I will choose origin point, and then I will define a point to use. Now I know point number 12's elevation is average in between the highs and lows of this area we're going to be surveying. So I'm going to pick number 12, and it will populate the combined scale factor based on the elevation of this particular point. Now if you want to, you may never use the ground coordinates at all. Again, we're just figuring out how to scale from grid to ground. But if you want to view ground coordinates, you may want to input a shift like I'm doing here. So just in case you change the views, you would know that you're actually looking at ground coordinates, but you may not ever use this. And then in the previous video, if you wanted to rotate to north, you could do that at this time. The main thing we're using is just point number 12 to calculate a combined scale factor for us to use for our total stations. So with this all filled out, we're good to go. We can press OK and then close out of here. Now just real quickly, under Edit Points, this is going to be viewed in the ground definition. So we go back to here. We can check this back to grid if we want. And we can also look at the latitude and longitude for the same datum of this particular grid, which is no trans. So let's just leave this on state plane because that's what we're going to be working in. So next, let's disconnect from the GPS and hook up to this total station. So let's disconnect. We'll connect to the manual total station. And now let's set our backside up. We're going to be surveying on the ground with the total station, but we want all of our measurements to be scaled back on the grid to match all the other coordinates. So we'll go to backside. We'll choose our backside point, which I can go to the map. Let's zoom back in. We're going to be occupying number 11, and then we'll backside. Zoom in a little closer, number 17. And let's click Next. There's our bearing. I'm going to zero set the gun, and I am going to measure this backside distance also to check. Now let's go ahead and hit set, and then it's asking for the distance. Now this particular distance that I enter in that would be measured on the ground is the ground distances. So it actually is 1574.06, this populated because I practiced this before. But the grid distance is 1573.86, if you remember when we did the inverse. But I'm going to say we're measuring this distance. I hope this is not confusing. So I measured the backside. Let's see how we checked. Notice that we have no horizontal error. So it scaled this distance that I measured on the ground to match. So I actually hit that point perfectly. We can look at that a different way also. Again, edit, well not edit, let's go to calculate an inverse, point to point, between 11 and 17, if you can remember those distances. This is the ground results. That's what we measured and plugged in. But notice also now we have our grid results. 1573.86, 859. Again, let's look at this a different way. Let's go to stake points. My design point I want to stake is my backside point. So here is the design distance, 1573.86. Let's measure 1574 on the ground, 0.066. Just take a look at that one more time. Grid distances, ground distance. We're going to measure that. We'll click OK. Now, here's our in and out to the total station, 0. So it took that distance on the ground, scaled it so I could accurately stake out points that are on the grid. So that concludes video number 17. I want to thank you for watching, and if you have suggestions for other product features that we might need more help on understanding, please let me know and we'll see what we can do. Thank you.